So hello guys, welcome again. This is Learn West Africa in a series of our videos where we are bringing to you the past questions that has been tested by Cambridge International Examinations with reference to your Pure Maths 1. Now in this series of videos that you'll be looking at in this section, we'll be focusing on circular measure. Radian measure, as you know, how you can use the radians and the degrees and how the other aspects of parts of circles can be tested. That is the sectors, the arcs, the chords, the segments, and all those other aspects. I'm sure you're pretty enjoying our videos. You know what I want you to do? Keep telling your friends. Keep inviting all the people or your friends, all the guys you are with in school to come and hook up to Learn West Africa. Go to our YouTube channel, and as you can see, most of our videos are there. Remember to like them, okay? And also subscribe so that anytime we drop any of these videos, you'll be the first one to know, and also most of your friends. If you have any questions, just reach to the comment section and put your comments there. We're also on Facebook, Instagram, and all the social media handles. I'm proud that you guys are benefiting from what we're doing, and keep supporting us so that we can keep on giving the best of the best to most of you. You're welcome. Let's go, circular measure. Summer 2015, question 5 QP11. A piece of wire of length 24 centimeters is bent to form the perimeter of a sector of a circle of radius r centimeters. I. Show that the surface area of the sector a centimeter squared is given by a is equal to 12r minus r squared. Okay, so in the first of our problems, as we have seen, as you were introduced to these aspects in our first of our problems, for question 5 QP11 of circular measure, summer 2015. The question is asking us that we have a piece of wire which is of length 24 centimeters and it is bent to form a perimeter of a sector of a circle of radius r. And we want to show that the area of the sector is given by a is equal to 12r minus r squared. So a piece of wire that is bent, okay, of length 24 to form a sector. What is the area of this sector? All right. So we'll try and make do with an example in here to help us to see. So this is how a sector basically looks like, right? So we have a sector like that. And this is the angle theta. Hope you're fine. This is the radius, so we can also refer to that as a radius. And here will be the length of an arc. Now you know for radian measure that when we talk about the length of an arc in terms of radians is r theta. So the length of this side is going to give you r theta, okay? So that is it, r theta. The length of an arc is r theta in radian measure. I would want to urge you again that if you are a bit unfamiliar with why in radians we say that the length of an arc is r theta, it will be best that you look at our revision course on circular measure where most of these facts are good in there. But here, because we are looking at the past question, there is that presumption that you already know a bit of those things, so we may not take a lot of time in trying to go into those details. But in circular measure and radian measures, the length of an arc is always the radius times theta, where theta is in radians. In fact, all the angles that we are using here is radians. That is why we call it radian measure, all right, or circular measure. So this is a sector, that is r, then the length of an arc is r theta. We are saying that a piece of wire is bent to form this sector. A piece of wire of 24 centimeters is bent to form this sector. What we can therefore deduce from this is that if you were to take the length of r theta and r, that should give you 24. So we can say that 24 is equal to r plus r theta. Hope you're okay with that. Okay, so what does that leave us with? We can therefore say that our 24 is equal to 2r plus r theta. Okay? All right, now the problem wants us to find the area of the sector. What is the area of the sector? What is the area of the sector? What is the area of the sector? Okay, so for the area of a sector, we know that the area of a sector, again, in radian measure, is always given by half r squared theta. That's in radian measure, half r squared theta. Half r squared theta. That is the area of a sector. So area of a sector is half r squared theta. That is it. So what can we deduce out of this? Now, if you look at this clearly, from the first relation, where we have 24 is equal to 2r plus r theta, from this, we can say that 24 minus 2r is equal to r theta, correct? Hope you're okay with that. All right, now let's look at this expression here. From A, the area of a sector is giving us half r squared theta. This is the same as half times r theta. Hope you're okay. Half times r theta. Now watch. R theta has already been found from the relation to be 24 minus 2r. Do you see that? R theta is equal to 24 minus 2r. So we can just replace the r theta and put 24 minus 2r in instead. So we are going to have half. We are going to have half, okay, times r, then times what? 24 minus 2r. So let's push that in there. What do we have? We are going to have 12r, okay, minus r squared. Okay, 12r minus r squared being the area of a sector. So we've been able to show that the area of the sector will be 12r minus r squared. That is what the question wanted of us, and we've been able to show that. So you look at it, you get the relation for the perimeter, okay, which is 24. You have 2r plus r theta, no problem. Then we also remember that our area of a sector is half r squared theta. You make r theta the subject out of that. Then you make a replacement. You do a substitution of r theta into that expression of the area of a sector. And that should leave you nicely at our area of a sector being 2r minus r squared, as the question wants us to find. So that is what the question 5 QP11 deals with here. Question 2, QP12, summer 2015. In the diagram, AYB is a semicircle with AB as diameter, and OAXB is a sector of a circle with center O and radius R. Angle AOB is equal to 2 theta radians. Find an expression in terms of R and theta for the area of the shaded region. Okay, so this is question 2, QP12 of summer 2015. Now this diagram was given you. Now look at the diagram carefully. I've just tried to re-sketch it to make it easier for you. So this is the point O, this is the point AB, okay, and a sector OAB is formed out of that. Okay, so the sector that we are referring to is OAB. The arc to that sector is going to be this. So the first curvature that you see, that crescent shape, the first one belongs to the sector. Now the problem also mentions that there is, it says that in the diagram AYB is a semicircle, AYB is a semicircle with center O, okay? The semicircle with AB as its diameter. So the diameter of AYB, like if AB is the diameter, then AYB is the semicircle that's coming from there. All right, that's what the problem mentions. And you're saying that OAXB, X is referring to the portion of the second one, is a sector with center O and radius R. And we are being told that AOB is 2 pi radians. And we want to find an expression in terms of R and theta for the area of the shaded region. So the area of the shaded region, we want to find an expression for that. We want to find an expression for that. All right, so let's look at it carefully. An expression in terms of R and theta for the area of the shaded region. Now look at the shaded region. We are being told that this is a semicircle. Do you understand that? ABY is from a semicircle. And we want to find that. So clearly, we want to find the shaded region. It is the area of the segment. The segment is ABX, or AXB, this particular segment here. Let me just identify it with this. I'm just trying to point. You get it? So the point where I've just indicated those dots, okay, those dots. This segment, if we were to take this segment out of the semicircle, if we were to take the segment out of the semicircle, guys, you should have the area of that shaded portion that we are interested in here. Okay? So now let's try and proceed and see if we can find the area of the semicircle. Then afterwards, we'll try and find the area of the segment. Then we'll take it out. That should leave us with the area of the shaded portion. Hope you're okay. All right, so let's look at the area of the shaded of the semicircle. Okay, now this is a radius r. So let's try and label the radius of the semicircle to be r. So we say that the area of the semicircle, okay, the area of the semicircle will be what? You know the area of a circle is pi r squared. Okay, so pi r squared divided by 2 is going to be the area of the semicircle. But in order to avoid confusion, we're not going to use this r. We need to code our r differently so that the r that belongs to the sector is different from the r that goes for that semicircle. So we call that r to this r1, okay? So that is going to give us pi r1 squared. Remember, so when I say r1, I'm referring to this distance here, r1. Okay, if this is a diameter, then r1 is like that, all over 2. Hope you are fine. We're okay. Now, we also need to note that r1, okay, is half of what? AB. You see that? Because AB is a diameter. If you divide the diameter into 2, you get the radius. So this particular semicircle that we are speaking about, its radius r1 is half of the diameter AB. But now guys, watch. Do you see that if you now focus onto this sector OAXB, the AB now becomes the chord. Okay? The AB now becomes a chord. Remember, when we say a chord, the chord is the line that touches on either side of a circumference of a circle without going to the center. Okay? When you have a line that touches on either side of a circumference of a circle but doesn't go to the center, that line is called a chord. And that's what we see here. Because this circle would have a center of O, and the line AB doesn't go to the center, yet it hits its circumferences. It is a chord. So AB is a chord. From our revision videos and what we know in radian measure or in circular measure, what is the length of a chord? So the length of chord AB, okay, which incidentally is also the diameter, what would it be? Now we know the length of a chord to be 2r sine of the angle there, 2r sine theta over 2. Do you get it? 2r sine theta over 2, where theta refers to the angle that has created that. So this is the general formula of a chord, 2r sine theta over 2. But now, if you look at the diagram carefully, the theta in this particular diagram is 2 theta. So we'll come and write 2r sine bracket 2 theta over 2. Do you get it? So the first one we are saying, I repeat, is the general form of a chord, 2r sine theta over 2. But in here, the angle that creates that chord, that creates that sector, has that angle 2 theta. So we will now come and do the proper replacement. So you have 2r sine 2 theta over 2. Now, that is going to leave us with the length of our chord, or our diameter, being 2r sine theta. Hope you are fine. So AB is 2r sine theta. Any problems with that? Any problems with that? Okay, so now, if that is the case, where our AB is that, what is going to be our R1? Our R1, okay, our R1 will therefore be half of AB. And now we know that our AB is 2r sine theta. So half times 2r sine theta. And guys, our R1 is going to give us r sine theta. Hope you are fine. So the R1, which refers to the radius of the particular circle that creates this semicircle, is r sine theta. Therefore, what is the area of that semicircle? Now, let me just take you back. The reason why we are finding the area of a semicircle, ladies and gents, it is because we want to find the area of the shaded portion. So when you know the area of the semicircle, then you find the area of the segment. Out of that, you get the area of the shaded portion. So all that we are doing in trying to identify R is because R is central to finding the area of the semicircle. If you do not know R1, which is the radius of this, you cannot find the area of the semicircle. So now that we now know the radius R1, which is the radius that belongs to the semicircle, being equal to r sine theta, we can say that the area of a semicircle, which you are looking for, area of semi-C, okay, area of semicircle is going to give you pi over 2 r1 squared, and this is our r1. So r sine theta all squared. Are you okay? So pi r1 squared, and our r1 is r sine theta. So we're going to have pi over 2, okay, r sine theta squared. So this is going to give you pi over 2 r squared sine squared theta. Hope you're okay. So now we have our area of our semicircle in terms of the r and theta. Because remember, the problem says that we should find an expression for the shaded region in terms of r and theta. And once we've been able to get the area of the semicircle in terms of r and theta, we are one step closer. So now we need to find the area of the segment. What is the area of a segment? What is the area of a segment? Again, if you have watched the revision videos, if you've not done that, I encourage you, go to our website at www.learnwestafrica.com, subscribe, and also register for the revision courses on your A-level mathematics on circular measure. I'm sure you find many practice examples there. It's there on our website, okay? And you can also go to our YouTube channel at Learn West Africa, and you can also look up some of the videos there. And remember to keep on sharing to your friends, okay? Okay, so let's continue with it. Now we have our area of a semicircle done. What is the area of a segment? Now, from basic theory, our segment AXB will be given by area of a segment. So I'll change the marker here. So area of segment, okay? What's the area of segment? It's going to give you half r squared, okay, theta minus sine theta. That's the area of a segment. General formula, area of a segment, where r is the general radius of where the segment is created. So, and our theta refers to that. But now if you look at this problem, the theta in question is 2 theta. So wherever we see 2 theta here, we'll replace it with that. Okay, so our area of our segment, this particular segment, is going to give you half r squared into bracket 2 theta minus sine 2 theta. Are you okay? So now, if we want our shaded region, which we know is going to be the area of the semicircle minus the area of a segment, that's what we found for the area of semicircle, and that's what we found for the area of the of our, how do you call it, of our segment. So what do? It makes it very simple. We can just put all of them together, can't we? All right. So our area of a shaded region. So the area of a shaded region, right? Let me just write the area of shaded region. Okay, it's going to be pi over 2 r squared sine squared theta minus, so we'll deal with this. Let's just try and push this one in here. So 2 to cancel that, minus r squared theta, okay, plus, because remember, because we are subtracting negative, will also end there. So plus half r squared sine 2 theta. Half r squared sine 2 theta. Are we okay? Are we okay with that? Okay, so that is it. It makes it pretty simple for us to be able to simplify. If you look at it carefully, you can realize that the r squared is very common. You have r squared in there. Okay, you have r squared in there. So what happens to that? We can just bring out the r squared. Okay, so we are going to have our r squared. Then this one's going to give you pi over 2 sine squared theta plus sine 2 theta over 2 minus theta. I hope you're okay. Let's take a second look at it. Very, very simple. So we've been able to show that our area of our region in terms of r and theta will be this. R squared, bracket, pi over 2 sine squared theta plus sine 2 theta over 2 minus theta. That is the end of question 2, QP11, summer 2015. Question 11, QP13. In the diagram, OAB is a sector of a circle with center O and radius R. The point C on OB is such that angle ACO is a right angle. Angle AOB is alpha radian and is such that AC divides the sector into two regions of equal area. I, show that sine alpha cos alpha is equal to half alpha. It is given that the solution of the equation in part I is alpha is equal to 0.9477, correct to 4 decimal places. Find the ratio of the perimeter of region OAC to the perimeter of region ACB. Giving your answer in the form K is to 1, where K is given correct to 1 decimal place. Find angle AOB in degrees. So question 11, QP13 of summer 2015. Now you have this diagram that was shown there to you. And it said that it is a sector of a circle with center O, okay? So this is a sector of a circle with center O. Now watch where the sector is. It's very important when you observe questions of that sort. Where is the center of the circle, or where is the center of the circle? It is O. So this is the sector. OAB is a sector. Now there's a perpendicular that travels from A to a particular point in here. That is C. It's perpendicular, hits it at 90 degrees, as you can see. Then there's an angle in radian, where the question quoted, where there's alpha radians like that. Now, what is the point? Now, it mentions significantly that AC divides the sector into two regions of equal area. AC divides the sector into two regions of equal area, which means that the area of this side is equal to the area of that. AC divides the sector into two equal regions. That's what the problem tells us, okay? We want to show that sine alpha cos alpha is equal to half alpha. That's what we want to show. Sine alpha cos alpha is equal to half alpha. So how do we establish that? Sine alpha. So let's try and find sine alpha. Okay, let's try and find sine alpha. Then we also find cos alpha. Okay, so we know that this is OC. Okay, this part is OC. Okay, that is OB. That is R. And this is our reference angle, theta. So from our basic SOHCAHTOA, trig ratios, a sine of an angle is equal to the opposite over the hypotenuse. Okay, opposite over hypotenuse. So it's going to have AC over R. So sine alpha is going to give us the opposite side, which is AC, all over hypotenuse R. Hope you're okay. Now let's look at cos alpha too. What is cos alpha? We know that cos alpha, K adjacent, is going to be the adjacent side over the hypotenuse. So that's going to give you OC over hypotenuse R. Hope you're okay. Any problem with that? Okay, so now if we try to multiply, okay, if we try to multiply sine alpha cos alpha, we are going to have a case where our AC over R times OC over R. What is AC over R times OC over R? That's our question. That's what we need to know. Okay. It is also significant and worthy of note that from this, we also know that our AC, okay, our AC is also equal to R sine alpha. Hope you're okay. And our OC is also equal to what? R cos alpha. Now, how do we connect AC and OC? Any idea? How do we connect AC and OC? Any idea? All right, now watch. It is important for us to also understand that because this is a right angle triangle, okay, it's a right angle triangle. It's a right angle triangle. We can also find an expression for the area, okay? We can find an expression for the area of the triangle. How do you find an expression for the area of the triangle? Now, for the triangle, okay, we can say that the area of the triangle is going to give you half base times height. Okay, so let's look at that. So the area of the triangle is going to give you half times the base. What is the base? The base is what? OC times the height, which is also AC, right? Okay, so we can therefore say that OC times AC over 2 should give you the area of the triangle, Okay, now watch what is happening here. From your earlier expression, we saw that AC times OC, okay, AC times OC was going to give you AC times OC all over R squared. Hope you are fine. That's the problem. The problem asks us to find the product of sine theta times cos theta, and that's going to give us AC OC over R squared. Now, if you look at this relation carefully, we also see the area of our triangle, okay, being equal to OC times AC all over 2. So what can we say out of that? We can therefore say that our area of our triangle, which is OC times AC all over 2, right, should be equal to half into bracket half R squared alpha. Do you get the reason why that is the case? Our area of our triangle is going to half R squared alpha. Now, this is the reason. You know, this is a sector, right? This is a sector. Remember, the question told us that this and that AC divides them into 2 equal parts, which means that if you take the area of the sector and you divide it into 2, it should give you the area of a triangle. This AC divides the whole area of the sector into 2 equal parts, which means if you know the area of a sector and you divide it into 2, the one part should give you the area of the triangle. From a basic understanding, what is the area of a sector? It's half R squared theta, where theta refers to the angle in radian. But here, the angle that we have here is alpha. So the area of our sector is half R squared alpha. That is what we have here. So this is the area of a sector. So half of that should give us the area of our triangle, which is OC times AC over 2. Okay? Hope you are fine. Okay, so with that, we can say that our OC times AC will be half R squared theta, because the 2 just go there and cancel them off. Okay? But now, watch in our expression. OC times AC is equal to half R squared theta. And we were looking for the product of AC or OC times AC all over R squared. So what we simply have to do is to take the whole of this and divide by R squared and see what we'll get. Okay? So our product of sine alpha over cos alpha, sine alpha cos alpha, which is AC times OC over R squared, is going to give us half R squared alpha all over R squared. And when the R squared takes off the R squared, we are going to get half alpha. And that should make sense to you. Hope you are fine. So let's just go to the procedure one more time. Sine alpha, AC over R, cos alpha, OC over R. The product gives us AC times OC over R squared. Now we note that the area of a triangle is half base times height. That's OC times AC over 2. This is the part that is most important for us to remember, because the question said that the triangle AC divides into 2, half the area of the sector, should give us the area of the triangle. Hence, that leads us to OC times AC is equal to half R squared alpha. Okay? And when we do that calculation, we will be able to get our half R squared theta all over R squared, giving us half alpha, which we have proven in the question to be the case. So that is what the problem tells us. Okay, so now that we've been able to see the value of, we've been able to show that sine alpha cos alpha is equal to half alpha. That we're going to show. Now the problem goes on to tell us that it is given that the solution of the equation in the first part, okay, is first part I is alpha is equal to 0.9477. That's what the question goes on to tell us. when it is corrected to 4 decimal places. Now, we want to find the ratio of the perimeter of the region OAC, the ratio of the perimeter of the region OAC, okay, to the perimeter of the region ACB. Okay, giving our answer in the form k is equal to 1, where k is correct to 1 decimal place. Hope you are fine. So we want to find the perimeter of the region. We want to show that the perimeter of the region OAC, okay, the perimeter of the region OAC to the perimeter of the region ACB. So this space that we are talking about, what is the perimeter of that? Now, that's the value of the alpha that we've been given in the problem. So how do you find the perimeter of that? Now, if you want to find the perimeter, guys, remember that from our calculations, okay, let's just quote a bit of that. Remember we said that sine alpha, okay, sine alpha is going to give you AC, opposite over hypotenuse. So sine alpha was opposite, which was AC over R. So our AC was R sine alpha, okay? And our cos adjacent over hypotenuse, cos alpha was going to be adjacent, OC over hypotenuse R. So our OC was going to give us R cos alpha. Okay. So we want to find the perimeter, the ratio of the perimeter. With the perimeter is going to give us OA plus OC. No, OA plus AC plus OC. Hope you're okay. So the perimeter that we are referring to, the perimeter is going to give you the distance around the shape. So this R plus AC, and AC is R sine theta. So R sine theta plus OC, R cos theta. Okay. Now remember that from this we can say that our R plus R bracket sine theta plus cos theta. What is sine theta plus cos theta? Already we've been given the value of our theta. Okay, so when we slot that in there, okay, when we slot that in there, we can get our values easily. Okay, now let's look at the perimeter of AC2, because that's what the question wants us to find. The perimeter of ACB. What is the perimeter of ACB? ACB. Okay, so we know AC to be R sine theta. Okay, we know AC to be R sine theta. Now we are now left with AB. How do you find AB? AB is the length of the arc. So we know AB is going to give you R theta. Okay, R theta, and this time we are going to have, so R alpha is going to be the value of AB. And we know AC already to be R sine theta. Hope you're okay. R sine theta. All right. So now we are left with BC. We are left with BC. Now we know that this is R. This is a radius of R. That one is going to give us a radius of R. And OC is R cos theta. Therefore, CB will be the result of taking R minus OC. R cos theta. Just take a second, look at it. It should make sense. So AB, the length of the of an arc is R theta, and our theta is alpha in this instance. AC, which we've already shown with the right angle situation there, is R sine theta. Then we have CB. This is CB. But we know that because it's the radius R, this side to OB to be R, and OC is R cos theta. Therefore, CB is what you get if you take OC from OB. Therefore, we say CB is equal to the radius R, which you find have here, minus R cos theta, which you have here. So what is the perimeter of the shape ABC? Okay, so that perimeter, okay, perimeter 2 is going to give us alpha plus R sine theta. R sine alpha, I'm sure we should have put alpha in place of all that. R sine alpha plus R minus that, okay? R minus R cos alpha, okay? So wherever you have the theta, you put the alpha there. So that's what you get for our relation, okay? So what do? Let's try and simplify that. Okay, so if you do a simplification of that, okay, the ratio of this to that by slotting in all the requisite values of alpha. Wherever you find alpha, you put 0.9477 there, okay? You will get the ratio being 1.10:1. That is what you get, okay? Which means that the perimeter of this shape is 1.1 times the perimeter of the first one. That should be okay. Then the last part says that we should find the angle AOB in degrees. What is the angle AOB in degrees? That should be pretty simple for us to find, right? AOB in degrees. How do you find AOB in degrees? AOB, that is alpha. We know alpha to be 0.947, and that's in radian, okay? But we know that 1 radian is equal to 180 over pi. So if you have 0.9477, what do you get? When you do the calculation there, you multiply that by 180, it should give you 54.3 degrees. Okay, so AOB, which is alpha, 0.9477 in radian, if you were to convert into degrees, you're supposed to get 54.3 degrees. So that brings us to the end of the exhaustive question 11 of QP 13. So you can just look at it. And remember that the text accompanies this. This is Learn West Africa, your #1 destination to learn and prepare for your Cambridge International courses. Just remember that you have to keep on subscribing to our YouTube channel, okay? Click on the notification button there where the bell is, so anytime that our videos are ready, you're going to have access to all of them, all right? And also invite your friends to like our page on Facebook. Okay, visit our website at learnwestafrica.com. I'm glad to have you. So